Hey guys, so at the end of our last presentation, we were talking about the classifications of different alcohols versus primary, secondary, tertiary. So I wanted to start out today's lecture talking about the link to health with alcohols and phenols. So one of the first ones I want to talk about is methanol or methyl alcohol, which is our simplest alcohol. It's found in many solvents and paint removers, and it can be easily oxidized to form formaldehyde when ingested and can cause headaches, blindness, and death. This is actually one of the main alcohols that we find in that can contaminate moonshine. When you are distilling ethanol, sometimes you produce methanol and it can come off first. And so if you're not careful and you contaminate your moonshine with methanol, that's what lead to alcohol poisoning in moonshine. So the other one we can talk about is 1,2-ethane-diol or ethylene glycol. So this is commonly used in the antifreeze and heating and cooling systems. It's also commonly used as a solvent for paints, inks, and plastics, and is used in the production of synthetic fibers. If ingested, it is extremely toxic. In the body, it is oxidized to oxalic acid, which forms insoluble salts in the kidneys that can lead to renal damage, convulsions, and death. Unfortunately, ethylene glycol tastes really sweet and yummy to animals, which is why it's very important to make sure that we keep antifreeze out of the reach of animals in our garages. And some other common phenols are phenols that are often found in the essential oils of different plants. And so as you can see, all of these different spices like vanillin and all of this, a lot of the notes in those flavors are because of these phenols. So let's talk about thiols now. So thiols are similar to hydroxyls or alcohols, but instead of an OH, we have an SH group that comes off the carbon. Often, unlike our nice smelling phenols, thiols typically are very stinky and have a very disagreeable odor. So it's often thiol is the odor causing agent that comes out of they are often found in cheese, onions, garlics, and oysters. And we actually add an agent, a thiol agent, to natural gas to make it easier to detect gas leaks, because natural gas actually does not have an odor. So what you smell when you say you smell gas is actually a thiol agent that we add to the gas. So thiols are known as mercaptans, and they are, again, a family of sulfur-containing organic compounds that have the thiol SH group. In the IUPAC naming system, thiols are named simply by adding thiol to the alkane chain name of the longest carbon chain and numbering the carbon chain from the end nearer the thiol group. So very similar to what we have already seen. Now, another molecule that I want to talk about very quickly is ethers. So ethers actually have an oxygen that breaks up between two carbon groups on an acyl or aromatic ring. And so we give it a common name is the acyl name of the attached groups followed by ether. So for example, sorry, I'm having a hard time seeing this screen. We have methoxy methane or methoxyethane or methoxybenzene. So if you notice, we name the first or whatever is our shortest chain, that will be our methoxy, and then our longer chain would be like our normal alkane. The other way we can name it is naming the two chains as acyl groups followed by ether. So dimethyl ether, ethyl methyl ether, or methyl phenyl ether. All right, so let's practice this. Give the IUPAC name for the following. Let me get my little pointer out here. All right, the IUPAC name for the following. So here we can see it's an ether because we have an oxygen that's breaking up the 2 carbon chains. So the first thing you want to do is identify and write the name of the longest alkane chain. So on this side, we have 2 carbons, and on the right side, we have 1, 2, 3, 4 carbons. So 4 carbons is our longest. So that is going to be butane. And then identify and write the name of the shorter alkane chain preceding the parent chain. So here, this is our shorter chain. That's 2 carbons, so that's ethane. So we have butane, ethane, and then we change the suffix of the shorter chain to oxy to identify the location based on the parent chain. So butane, ethane, oxy, ethoxy. So ethoxy butane or butane ethoxy. All right, so butane, ethane, 1-ethoxy butane. All right, so why don't y'all pause here and go to question 3 on mastering chemistry and answer that one. You can also go back to question 1, part C, and answer the question for naming your thiol. All right, when you're ready, come back. So ethers are very commonly used as anesthetics. So anesthesia is when we have a loss of sensation and consciousness. A general anesthetic is a substance that helps block signals to the awareness centers of the brain and gives the patients a loss of memory, a loss of feeling of pain, and an artificial sleep. So a very common one is this molecule right here, which, as you notice, you see the oxygen is breaking up to the 2 carbons. So it's furane or isoflurane. So furane, isoflurane is an inhaled anesthetic that is very effective for clients. Also, in an alcohol-containing sanitizer, the amount of ethanol is typically 60%, but can be as high as 85% because alcohols are flammable. Hand sanitizers are a fire hazard at home. So again, another important, medically important alcohol is the ethyl alcohol found in hand sanitizers. So let's talk about some of the physical properties that we see in alcohols. So because there's a large electronegativity difference between the oxygen and hydrogen atoms of the hydroxyl group, the oxygen having a partial negative charge, the hydrogen having a partial positive charge, that's going to make us be able to form hydrogen bonds between the hydroxyl group of the alcohol and other water molecules. Or hydrogen bonds with other alcohols, and that's going to help increase our boiling point because you have more intermolecular interactions once we've introduced that ability to create hydrogen bonds. So compared to alkane chains that do not have a hydroxyl group, the alcohol counterpart will have a higher boiling point. Now, ether molecules, they're able to form hydrogen bonds with waters, but not with each other because they don't have a hydroxyl or a hydrogen coming off of that oxygen. So they can receive hydrogen bonds, but they can't donate hydrogen bonds. So you're not going to see as much of an increase in the boiling point of an ether counterpart as you do the alcohol counterpart. So again, yeah, hydrogen bonds cannot form between ether molecules because they are not, there's not any polar hydroxyl groups there. There's no hydrogen coming off of the oxygen in the ether to form hydrogen bonds. So if we want to think about a trend, alcohols with similar masses are going to have higher boiling points than ethers because the alcohol requires higher temperatures to break those hydrogen bond networks between the different alcohol molecules. Remember, ethers can't form the hydrogen bonds, alcohols can't. The boiling points of ethers are going to be then similar to those of their alkane counterparts because neither alkanes or ethers can form hydrogen bonds with each other. In terms of solubility, again, alcohols have that very polar hydroxyl group and can form hydrogen bonds with other alcohol molecules and with water. So they typically are fairly water soluble when they have 1 to 3 carbons. If you get to longer alkane chains, then you're going to start to lose that solubility in water, because basically you're kind of having this tug of war between the hydrophobic nature of the alkane chain and the hydrophilic nature of the hydroxyl group. So the hydroxyl group can only help solubilize that alcohol to an extent. If that chain gets too long, then we're going to lose that solubility. Now, ethers, while they can't form hydrogen bonds with each other, they can form hydrogen bonds with water. So it's going to be fewer hydrogen bonds than compared to the alcohol. So we're going to be slightly more soluble in water than we are with the alkane chain, but they're not quite as soluble as the hydroxyl, right? So if we sort of ranked everything, the alkanes are going to have the least solubility, followed by ethers, followed by alcohols to the most water soluble. Phenols, which are often used in aseptics, are only slightly soluble in water. Again, yes, we have that very hydrophilic hydroxyl group that's going to help increase our solubility, but because we have this like bulky hydrophobic aromatic group, we're not going to be quite as soluble. However, there's something interesting that phenols can do. This hydroxyl group on a phenol is actually considered a weak acid, and it can deprotonate. And so what that means is we can actually form a negatively charged ion, which is going to further increase our solubility. So again, if we can do some comparisons in terms of physical properties, if we look at the boiling points of alcohols versus ethers, notice here our boiling point is going to increase as the chain length of our alcohol increases because we have more intermolecular interactions occurring. We see the similar trend with ethers. As our chain length increases, our boiling point increases. But if you compare similar chain lengths between, say, the alcohol with 2 carbons and the ether with 2 carbons, notice there's a very big difference. The alcohol has a much higher boiling point than the ether counterpart. And again, that's because of that ability of the alcohol to form hydrogen bonds with each other versus the ether, which cannot form those hydrogen bonds. And we're going to do an activity on Monday as a review to sort of help us pull all of this together, okay? So if it's confusing right now, don't worry. We'll pull it all together. All right. Why don't you take a moment and sort of review these concepts on questions 4 through 5 on Mastering Chemistry. So pause the video, and then when you're ready, come back and we'll continue our lecture. All right. So let's talk about reactions that alcohols and thiols can undergo. So the first reaction I want to talk about is the dehydration of alcohols. So alcohols can undergo the loss of a hydrogen and a hydroxyl from adjacent carbon atoms from the same alcohol, producing an alkene and a water molecule. So dehydration, when heated with an acid catalyst, is again, we're going to pull a hydrogen and a hydroxyl off of the same carb or off of adjacent carbons in order to get an alkene. So we start with our alcohol, we remove a hydrogen and a hydroxyl from the neighboring carbons, and we end up with an alkene and water. All right, so why don't y'all practice predicting the product of that? Now, if you get stuck with number 6b, don't worry, we will talk about that in class, okay? All right, so one of the questions you may have had, especially if you looked at 6b, is which way does the double bond go in the dehydration reaction? So when we have a secondary or tertiary alcohol, we can actually get a mixture of products. So we can end up with a less substituted alcohol or a more substituted alcohol. And then we can also get a mix of cis or trans when we talk about the more substituted. So the least substituted product is going to happen less often. So it's a minor product. So our major product is going to be the more substituted product. And then often it is the trans that is the major product compared to the cis. So when I talk about the less substituted product, what I am talking about is when we undergo the dehydration reaction, we're always going to lose the hydroxyl from this carbon right here. Now the question is, which hydrogen do we lose? Do we lose the hydrogen off of this carbon, or do we lose the hydrogen off of this terminal carbon? So the less substituted alkene is when we lose the hydrogen off of this terminal carbon. So notice when we say less substituted, if we look at this carbon here has 2 hydrogens coming off of it. So that's less substituted than, say, this product. So the more substituted product is if this hydrogen is lost instead of this one, right? So we lose this hydrogen in order to make water, and we form our double bond between carbons 2 and 3 versus carbons 1 and 2. So in carbons 2 and 3, if you notice, both of these carbons have 2 carbons coming off of them and just one. So one carbon-carbon bond and one hydrogen-hydrogen bond, versus the less substituted alkene where we have a carbon-carbon, carbon-hydrogen bond on this carbon, carbon 2, but on carbon 1 we just have 2 hydrogens. So carbon-hydrogen, carbon-hydrogen, and carbon-carbon. Okay, so see the difference, right? We have more substitutes here, less hydrogens. Here we have more hydrogens, less substitutes. Okay. Now again, we have 2 different products, right? We could have the cis product where the hydrogens are coming off of the same face of the double bond, or we can have the trans product where the hydrogens are coming opposite sides of the double bond. The trans product is always going to give you less steric interference, and so that's usually why it's always going to be our major product. So overall, we can get 3 different products in this reaction, but the trans most substituted product is going to be the one we see the most often. And again, in class, I can kind of write this out on the board to help make it a little clearer if it's not. Next slide. Oh, would you go to the next slide? Is there no sound? Oh. So another reaction that alcohols can do are oxidation reduction reactions. So in organic chemistry, an oxygen reaction increases the number of carbon-oxygen bonds by the addition of oxygen atoms or the loss of hydrogen atoms. So we can either sort of increase the bond order between this carbon and this oxygen, or add an additional oxygen, or we can lose hydrogens off of the carbon that is bound to that alcohol group. Now, reduction is the opposite. So reduction reactions reduce the number of bonds between carbon atoms and oxygen atoms, and we usually are adding hydrogens. All right, so for example, we can have a primary alcohol that gets oxidized to form a double bond between that carbon and oxygen. Notice we lost a hydrogen off of this oxygen, and we also lost a hydrogen off the carbon. So we lost 2 hydrogens and we increased our carbon-oxygen bonds. We can further oxidize that to add another hydroxyl group off this carbon, displacing this hydrogen. So we get what's called a carboxylic acid. And then, like I said, we can get different ratios of oxidation based on whether we're starting with a primary alcohol or a secondary alcohol. So let's look at that. So for the oxidation of primary alcohols, Alcohols undergo oxidation, increasing the number of carbon-oxygen bonds. And to indicate the process of oxidation, we use this symbol right here. So the bracket with an oxygen in the middle, placed over the reaction arrow. So primary alcohols are going to first be oxidized to form what we call an aldehyde, right? So we're going to lose a hydrogen off of the oxygen. Notice that here. And then we're also going to lose one of these hydrogens off of carbon, and we're going to create a carbon-oxygen double bond. So we're going to go from a primary alcohol to the aldehyde. Now, aldehydes can be further oxidized another time to produce what we call a carboxylic acid. So here we're going to lose the hydrogen off of the aldehyde carbon, and we're going to replace that hydrogen with another hydroxyl group. And so notice we have now 3 bonds between carbon and oxygen atoms, and we have lost another hydrogen to form this carboxylic acid. Now, secondary alcohols can only be oxidized once, and they will be oxidized to form what we call a ketone. So again, notice we have our secondary alcohol. When it undergoes oxidation, we're going to lose the hydrogen off of the carbon, and we're going to lose the hydrogen off of the oxygen, and we're going to create a double bond between that carbon and that oxygen to form what we will call a ketone. Now, tertiary alcohols cannot be oxidized because we do not have a hydrogen off of this carbon that can be lost. So no product is formed. All right, so remember, if you want to review this, oops, I can't go backwards, but if you want to review it, remember primary alcohols can be oxidized twice, once to form the aldehyde and then a second time to form a carboxylic acid. Secondary alcohols can only be oxidized once to form what we call a ketone, and then tertiary alcohols will produce no product undergoing oxidation. Thiols can also be oxidized. When this happens, the hydrogen atom is lost from 2 thiol groups, and this is going to produce what we call a disulfide bridge or a disulfide bond. And so this is a very common reaction that happens in proteins, specifically proteins in hair. So the amino acid cysteine that you'll learn about later this semester has a thiol group coming off of it, and it can undergo oxidation to form the disulfide bridges. And so people who have lots of cysteine residues in their hair follicles actually have curlier hair. We can reverse this by reducing the sulfur groups in order to put the hydrogens back on. And so if we are chemically doing this, then we are using chemical straighteners to straighten hair. You can also use heat to do it, but it's not putting the hydrogens back, it's just breaking the disulfide bridge. And so that's why when you do heat straightening, it doesn't last very long. Those disulfide bridges will reform, where chemical straighteners can last a little bit longer because we actually do put the hydrogens back. So in order to help link the oxidation of alcohols to health, one thing you can think about is the formation of acetaldehyde, which is also known as ethanol. This is produced from ethanol in the liver when it is oxidized in the body, and then it's further oxidized to acetic acid, which is converted to carbon dioxide and water in the citric acid cycle. So acetaldehyde will continue on to more reactions to form CO2 and water. So liver enzymes will eventually break down ethanol, but the aldehyde and carboxylic acid intermediates, these guys right here, can cause considerable damage to liver cells. So this is how we can get liver damage due to excessive drinking, and it can also add to the negative side effects that we feel from a hangover due to the accumulation of these acetaldehydes. All right, so why don't y'all go on to Mastering Chemistry and work questions 7 through 8. And when you're ready, come back. All right, guys, so that's going to wrap us up for this chapter. Just as a reminder to look at this concept map, because that's a great way to kind of remember what this chapter covers. So we talked about 2 different 3 different functional groups. We talked about Alcohols and phenols, put those together with hydroxyl groups. We talked about thiols that have the sulfur groups on them. And we also talked about ethers where we can insert an oxygen between two carbons. We talked about how thiols can undergo oxidation to create disulfide bridges. We talked about how alcohols can undergo dehydration and oxidation. When we dehydrate an alcohol, we're going to form an alkene. When we do an oxidation of alcohols, we can get different products based on whether we're talking about primary or secondary alcohol. And then one thing I didn't also talk about, but we can combust alcohols as well. And so that reaction is going to be the same that we see with alkanes. Alkenes are alkynes, except remember there is an oxygen you need to account for in the alcohol when you're balancing your chemical equations. All right, guys, so that's going to wrap us up for the rest of this chapter. Again, if you have any questions, write them down and be ready in class when we meet again for us to review. All right, hope you guys have a great weekend. Bye.